So what I'm going to talk about is hierarchical self-assembly of desiccation crack patterns in clay. That is just the mud cracks you see here, something like that. And we are interested in the effect of an electric field on these crack patterns. My collaborators in this work are Ankita and Dijkstra. They are PhD students, and Dijkstra is teaching at the college in Kolkata. Tapati Dutta is here. You will hear talk later on. So, about the mud cracks. Now, when some paste type of colloidal suspension dries on cracking, dries and cracks, the crack pattern formed depends on many factors, like what is the composition of the paste, what is the solvent and substrate, and also the external conditions, the temperature, humidity. These determine the rate of drying. And besides, you can also have some external fields, like an electric field or magnetic field, and also mechanical perturbations. The system can be rotated or vibrated before drying, and that gives characteristic patterns. Here you see two differences due to the composition. This is clay, pure clay, and here this is 90% clay mixed with some polymer. So now, right now, we are interested in the electric field effect. Now, for our experiments, we do not use natural clay because that is not well characterized. We use a synthetic clay, which is called laponite, and it is quite mono-disperse. The particles are very small, nano-sized, as you can see here. And this is the chemical composition. It is all very well known and quite well studied. So what happens when we dry a paste of laponite? Now, we have been doing this work for quite a number of years. In our earlier experiments, the setup we used for the electric field had a cylindrical geometry. And this is how we make the suspension and so on. But the setup was like this. In a Petri dish, we had two electrodes made of aluminum foil, one fitted at the periphery and one a rod-like at the center, the counter electrode. So the electric field is radial or cylindrical. And what happens when a field is applied is like this. The cracks, if the center terminal is positive, the cracks appear from the center, these are the cracks, and they move to the periphery. And if you have the oppositely directed field, that is the periphery is positive and the center is negative, in that case also the cracks appear from the positive. In this case, that is the periphery. So the cracks have started here, but as you see, they do not go right up to the center. This is what we had earlier. And obviously here, the electric field is not uniform. It is stronger at the center and weaker at the sides. So why we chose this setup is that it had one advantage, and that is that the boundary conditions become very simple, though the field is non-uniform. In our later experiment, what I'm going to talk about now, we have a uniform field, but here the boundary conditions create some problems. So now the setup is like this. We have a rectangular box made of acrylic or perspex, and at one end we have the positive electrode, at the other end the negative electrode, and inside it we place the clay and apply the voltage. If the voltage is 0, that is no field, the cracks look somewhat like this. There's no particular order, sort of random. And what happens if, now the problem that I spoke of is that at these two boundaries, the boundary conditions are not well defined. So we have chosen a large aspect ratio. The length is much larger than the width of this box. And we ignore the two edges. When we analyze the pattern, we cut off the two edges and look only at the central portion. And in the central portion, we can assume that the equipotentials are parallel lines, uniformly spaced. And this is what we see. After 12 hours of drying, you can see that from the positive electrode, the cracks have started to appear. And after 20 hours, these cracks are proceeding, but what is interesting is that they are not proceeding straight. The neighbors are merging together, and so as we go on, the number of cracks is gradually decreasing. Here, they have almost reached the other end, and you see that this is after 24 hours, and you can see that here a very characteristic structure is emerging. It looks like a number of trees or a forest, you may say, and all these trees have many, many branches which go up to the top. This is for 80 volts. We've also changed the voltage. Now, this is a pattern after complete drying. And here what happens is that some more cracks appear from the negative end, and these are due to desiccation. They are not the effect of the electric field. They can be identified because they are coming from the negative end, and because we want to study the effect of the electric field, we have separated these cracks. That is, the field-induced cracks are these ones which form the trees, and the desiccation cracks are these which sort of prop up the trees. So what we did is, before the analysis, we marked out the desiccation cracks, pure desiccation cracks, and we artificially removed these. So this is the pattern we are going to analyze. Now, so these are the steps how we are doing the analysis. This is the full image. We have the edges cropped, as I explained already. And because the number of cracks is going down as we go towards the, from positive to negative end, we have divided the system into some parallel segments, into 7 segments, and we measure the length of cracks in each of these segments and see how that is changing. This is what happens if we increase the voltage. For 50 volts, this is the pattern, 70, 80, and so on. We can go up to 130. Sometimes the pattern, there is some statistical effect, so the pattern doesn't look exactly as we expect. But in general, you can see if you compare these two, that as the voltage increases, the number of cracks is increasing greatly. This is a more dense forest with a larger number of trees, and the trees have more branches. And if we measure the crack length in each of the segments, then, and if we plot it like this against the distance between the positive and negative electrode, then we get something like this. The crack height, the crack length, it is initially the largest step, and in steps, the total crack length is going down, and there is also the effect of the varying voltage. So the lowest voltage, more or less we are getting the lowest step in each case, not exactly, but on the average. And for the highest voltage, the steps are high. So this is our analysis of the pattern. To explain this, we argue in this way that when the laponite or any clay is in aqueous environment, usually it gets charged. The positive ions leave the large clay particles and leaving the bare laponite disk with a net negative charge. And the small counter ions, they are free to move. So in the electric field, the counter ions will move towards the negative electrode. And the bare clay particles which are left, they repel each other, and that creates the cracks at the positive electrode. That is what we are suggesting. And we also did a very simple calculation based on this model. I'm not going into the details of the model here, but these broken lines, these are what we got from the calculation, and you can see that if we compare with our experimental steps, then this is more or less in agreement. After some point, the crack, number of cracks or crack length does not decrease any further. It goes right up to the other end. As we noticed that the tree trunk, at some point, it stopped, there is only one. So finally, we have only this number of cracks which reach the other end. This is the more or less the work, the experimental work which I wanted to describe. It is not yet published and still under revision. But why am I speaking about this here? That is because I thought, in a sense, this type of problem will be of interest to the audience here, because if we look at natural systems, there is such a proliferation of these tree-like patterns everywhere, which are described as fractals. This, of course, is a lightning pattern, river network. And this is a fracture pattern, but it is not desiccation fracture. This is from the very well-known book on by Derek Hull on fracture. It's called Fractography. And on the cover of the book, they have this nice crack pattern, which is called the river line pattern. This is brittle fracture, and it arises from a mechanical stress, not drying. But again, you have this very similar type of character. And it seems that nature has a sort of preference for systems to evolve in this way, in tree-like patterns, which are describable by fractals. So, when we think of entropy, we naturally expect that entropy will lead us to the direction in which systems are evolving. So if you think of all those systems as belonging to this idealized family of fractals, which are mathematically described as the Bethe lattice or the Cayley tree, is there some basic principle of entropy which leads us to all these patterns, which have that thing in common, that they are all tree-type patterns? So I have expected that maybe someone from here can give me some suggestions whether we can try to explain our work on the basis of ideas which involve entropy. So that is all I wanted to say. We've been working on fracture, desiccation fracture for many years, as I said. And this is I'm giving a little advertisement for a book we have published together with some Japanese and Canadian authors. And so that is all. And thank you very much for your attention.
Thank you.
Thank you very much for the nice talk. I have one question. In the process where you apply a field in the lapidary clay, wouldn't you expect also that there would be electroosmotic flow?
Actually, we wait till the gelation goes up to a certain extent. If it is completely liquid, then it's difficult to do the experiment, and there would be electroosmosis and gelation.
Sure, but if you have a gel, then the matrix is fixed, but the fluid can still be transported. So I would expect that you have an excess of fluid moving towards the negative electrode and maybe evaporating on that side. So that might explain why the positive side is getting dry more quickly.
That is a fact, but what we tried to verify is that actually what we find is that one end of the sample does get thicker than the other.
Yeah.
And it is the negative end which gets thicker than the positive.
Yeah.
And to verify that this free pattern is not the effect of that, what we did is we forcibly changed the gradient. We tilted the surface so that the other end becomes thicker. So keeping the field direction same, we gave a tilt to the base of the system so that the other end becomes thicker. But in that case, we also found the same kind of pattern with the larger number of cracks coming from the positive end.
Thank you.
Any more questions?
It's on.
No, it is just a natural drying process. Or for example, if you take the lightning pattern, the number of cracks, it goes on increasing as it progresses. But in the voltage-induced drying mechanism, the number of cracks are decreasing. I mean, it seems counterintuitive.
There are both examples. If you think of a river network, when it is the river is forming, the tributaries are a large number of tributaries. They come and coalesce and give you a big river. And when the river is meeting the sea, you have that distributaries. So it goes both ways. If you think of our system of veins and arteries, you can have the branching can be in both ways, but that pattern with the number of branches increasing or decreasing, that remains similar.
More questions? Okay, if not, let's thank the speaker for the nice talk and all speakers of this session.